Hi, my name is Anastasios Nanos. I'm from Robificus, and I'm going to show you a short demo of vAccel, how to get the code, how to build it, explain the rationale of the framework, run a couple of simple examples, and describe how we have deployed a vAccel-enabled OpenFast function in a sandbox container on Kata containers and Kubernetes, and how this function can enjoy hardware acceleration without access to a hardware accelerator device. First, let's go to the vAccel tutorials repo on GitHub. This repo holds a number of lab exercises where we show how to build the framework and how to run simple operations. Let's go ahead and open a terminal. The first thing to do is to get the code and go into the relevant directory, prepare the build files, and build it. So now we've got a shared object, the core framework, essentially a library that programs can link against and use vAccel. A simple example is the one shown here. So it's a pretty straightforward C program where we initialize a session. We call a vAccel API operation, the vAccel no operation. You can imagine what that does, nothing. And we free the session that we just created and exit. Now, to compile this program, we build it and link against vAccel and libdl, and we're ready to run it. When we execute it, we see that there's an error message referring to that this operation is not supported. To shed some light into the error message, we can enable debug, more debug information through an environment variable. So if we run the same command with debug enabled, we get the following. We see that the library is initialized, a new session is being created, and there's a warning about a non-existing plugin. What that means is that although we have called an API operation, the vAccel API operation, there is no plugin that implements that. Let's go ahead and build a plugin that implements that. We have in the base source tree, we have no plugin, which is a debug plugin that does nothing. Let's enable the building of the plugin and rerun it. The result of this operation is another shared object, essentially this plugin, and we can trigger the use of this plugin at runtime using another environment variable, vAccel buckets. So if we run the same command with this environment variable, we get no error. We see that the library is initialized. There's some extra debug information here, that the plugin has been registered. There is a number of API calls that are supported in this plugin, and essentially what is being executed is the no operation, and we get this printout. So what we've seen here is that we we can call a vAccel API operation. We can create a user space program that calls a vAccel API operation, and we can build separately a plugin that implements this API operation. Let's go ahead and see a more realistic example. So one of the API calls of vAccel is image classification. So we build again a simple user space program that enables a session, gets some input from the command line or from an external file, and calls the vAccel image classification API operation again, and freeze the session on exit. Now we can run this operation. It's embedded in the examples, so we just have to enable the building of the examples, rerun make, and call it using an image as input. Let's go ahead and get nice image of a dog. Let's go ahead and run the classification operation. We get the file name and the number of iterations. So what we get here is, again, the initialization of the library and the plugin, and the loading of the plugin, and we've got the session creation and some extra information about the image, which is actually called from the No plugin. So up to here, this is our user space program. Here it's the core library that looks for a plugin that implements this API operation, and this is the actual plugin execution that dumps some information about the image, and this is again our user space program that prints out the result given from the plugin. And a more realistic example would be using a plugin that accesses a hardware accelerator, not just the NOP operation, the NOP plugin, but a real-life image classification operation. Let's go ahead and log into a machine with a GPU and try that out. So we are on a machine with an NVIDIA GPU, the GeForce RTX blah. Let's get the image again, and we have vAccel installed on this machine. So we have built a backend, a plugin for the Jetson inference framework from NVIDIA. So we will use this plugin. We can enable debug to see what's going on. vAccel is installed on opt vAccel, and let's go ahead and run the classification operation. As we can see, the output is different. However, the first output is the initialization of the library, the loading of the plugin. So the Jetson Inference plugin supports three operations: image classification, detection, and segmentation. This is the message of the successful load of the plugin, and this is the initialization of the session. And the framework sees that we called image classify. The implementation is found in the plugin, and then the rest of the output is from the plugin and the tensor inference framework. So we can see that it's based on the TensorRT. There is a couple of initialization steps, and we end up with the actual classification, the accuracy and the confidence. So it's the classification tag is a golden retriever, and we get that from the user space program, from our classify program. So why is this useful? The decoupling of the API operation from its implementation is useful because we can call that from a VM. We have built a vIRT.io plugin where we forward over a transport layer the actual API operation. So from the VM, we call vAccel image classify, and this gets forwarded to the host, where the host has access to a hardware accelerator. It gets executed, and the results are forwarded back to the VM. Let's go ahead and see that in action. We go to the vAccel installation directory. We inject the image in the rootfs, some cleanup, and we execute the VMM, the Firecracker VMM. So we've got the vAccel backend, libvAccel Jetson, we've got debug enabled, DLV library path, and the execution of the VMM. Now we're in the VM. We see it's a dual core VM with 4 gigs of memory. We've got the image there and the vAccel installation directory there. So let's go ahead and call classify. So we specify the vAccel backend as libvAccel vIRT.io, the plugin that we mentioned earlier, and execute the classification operation. Now the output is mixed both from the host and the guest. So this is output from the guest. The plugin is the vIRT.io plugin, registering the various API operations. So we can see that there's the image classification implementation is found in the vIRT.io plugin, and then this is actually a host message. So the implementation, this is from the host, and this is from the guest. And we can see some similar output like before. However, we get the same result and the same classification tag. Now, if we disable debug from the VM execution, the output might be a bit cleaner. Let's go ahead and rerun that. So let's set the vAccel plugin and rerun the classify operation. Now the debug output is only from the guest, where we see that a number of functions are registered, the plugin is loaded, so looking for the plugin implementing image classification, it's found in the vAccel plugin, and then it triggers the execution on the host. After the execution on the host, we get the printout from the guest, which gets the classification tag. OpenFaaS is an open source serverless framework that can be deployed in Kubernetes. It has a number of control plane containers and spawns functions as containers on this orchestration framework. Now, in our setup, we have used Kubernetes runtime class mechanism so that we can spawn sandbox containers and enable better isolation between functions, which is useful in multi-tenant setups. We use kata containers for this functionality, and we have also tweaked the kata containers runtime to enable vAccel. Let's see that in action. So let's log out of the VM and let's have a look at the setup. So we've got a Kubernetes cluster with a number of nodes, various architectures, and there's a namespace for the OpenFaaS control plane, where there are a number of containers for the gateway, the scheduler, the queue, etc. And there's another namespace for the functions. There are a number of functions running or not running on various nodes, etc. Now, what we've built is a simple image classification function available on GitHub, also on our organization. And we built that using a Docker file. So, as we can see in this Docker file, we install a vAccel release. We build a simple function, a simple C program for the actual function. We use the watchdog, a core component of OpenFaaS functions, essentially a web server that forwards requests from a specific port, HTTP requests, to any kind of program running in this container. And we also set some variables related to vAccel. So the actual function running on this container is the same as the classify example. There's only a tweak to get to translate the HTTP payload, the input data, into standard input, so that the API call can get some kind of input. So again, the function is a simple vAccel program. We initialize a session, we call the vAccel API operation, image classification, and we free the session. Let's see that in action. In order to deploy this function, we use a standard OpenFaaS utility, FaaS CLI, with a descriptor file. We build that into a container image. We call that classify image. We define the process that the watchdog will run, and the relevant OpenFaaS profile. So we have created a custom OpenFaaS profile, that is bound to the Kubernetes runtime class, so that we can use our custom kata containers runtime where vAccel is enabled. So let's see if this function is deployed. We can see that it is running on the node that has the GPU, and in order to trigger it and showcase how that works, we have created a simple UI. So the endpoint, we have an ingress controller, so this can be accessed from the public internet. We can choose an image file, so we can go ahead and get the same image here, submit it, and we get the classification tag, we get some other statistics, and if we want to see what's going on under the hood, we can enable logs for the container function. We can resubmit it. We see that the watchdog replied with forking the F process. The F process is the pipe from the repo here, and we see the duration of the function, etc. So essentially what happened is that we have a sandbox container hosting a function, an open fast function, and we can see that using some Kubernetes CLI. So we've got this is the container ID, and we get a snippet from it, and we can examine the processes running from this snippet. So we can see that there's the container runtime, the handler essentially from container D. There's the Firecracker process, the VMM, the actual VM sandbox, and there's also the vAccel RT agent that provides access to the hardware accelerator that essentially does executes the commands to the hardware accelerator. For our final example, we will check the other mode of execution of vAccel, the exec plugin. So we have created an open fast function based on the subgoal filter operation and its CUDA implementation. So we've got a CUDA kernel, the subgoal kernel, which calls some helper functions, and as we have mentioned, we've got the packing and unpacking of arguments. So the process to enable the exec operation is to first have all the arguments in a specific structure, the struct vAccel, and on the backend unpack these arguments and call the actual operation, the actual library. So on the front-end side, we've got a simple C program. There are some helper functions, and the actual operation is again a generic vAccel program. So we've got the initialization of a session, the definition of the symbol found on the libified shared object that will run on the host, the actual path for the shared object, and the kind of arguments we want for input and for output. Now, this filter gets some text input, some numbers separated by new lines, and what it outputs, it does some kind of processing, some kind of filtering on the GPU, and it outputs the time it took on the GPU and the time it took for just for the kernel to run on the GPU. We call vAccel exec and we free the session. So this is the user space program that is running on the OpenFast function, on the sandbox container. Again, we can use another part of the UI, and to get some input, we've got some raw files here. We can get the full data set. Let's copy that, paste that here, and we submit it. So the reply for that is that the GPU process took 1.04 milliseconds, and the subcode kernel took 48 micros. The library used the libified application was libsubcode CUDA, and the actual symbol code is the subcode GPU unpack. Again, we can have a look at the container hosting the function, and we can also use the same command line for determining where this is running. So if we use the name of the pod, we can see that this is the kata runtime, this is the Firecracker VM, and the vAccel RT agent that enables access to the hardware accelerator. Thanks very much for watching. We will be more than happy to answer any questions, hear your thoughts and comments on the framework, on things that we could improve, or even help you to get vAccel running on your machines, on your accelerators. Thanks very much.